In this talk, we'll look at the different types of mass spectrometer and what applications they can be used for in medicinal chemistry and bioanalysis. In particular, we'll concentrate on the different mass analyzers that are available. The schematic shows the basic parts of a mass spectrometer. In a previous talk, we concentrated on the ion source and in particular electrospray ionization. Once ions have been generated, they need to be separated according to their mass to charge ratio, which is the role of the mass analyzer. As shown in the cartoon, there are many types of mass analyzer, and this is by no means an exhaustive list. Some shown on here, such as the magnetic sector instrument, were quite common in the past but are now only used for specific applications. Others, such as the FTICR instrument, a type of ion trap, are particularly expensive and are not therefore used for routine use. We'll therefore concentrate on the 6 different types of mass analyzer shown. In terms of learning outcomes, we'll explain how each type of instrument operates. We'll then look at their advantages and disadvantages in terms of their use in medchem, which mainly involves compound conformation, and in DMPK bioanalysis, which is predominantly quantitative. Finally, we'll show why most quantitative analyses are performed using either tandem MS or high-resolution MS. There are a number of different types of ion trap used in mass spectrometry, and we'll look at 2 of them in this talk. The electrostatic or Orbitrap at the end of the talk, but firstly we'll look at the 3-dimensional ion trap. This consists of a ring electrode with 2 end cap electrodes at either side. Space in the middle of the ring electrode is known as the trapping region and usually contains a buffer gas such as helium. Ions from the source can accumulate in the trapping region before voltages applied to the electrode cause the ions to be ejected and detected to create a mass spectrum. Ion traps are also capable of MSMS and indeed MS to the N operation. This cartoon at the bottom of the slide shows how the ion trap works in MSMS mode. Ions of different mass to charge represented by the different colors accumulate in the trapping region. At a certain point, when sufficient ions have been accumulated, all the ions are ejected from the trap apart from the one that we're interested in, the precursor ion. This is then fragmented in the trapping region before voltages again applied to the electrodes cause the fragments to be ejected from the trap to produce a product ion spectrum. It's also possible to withhold one of the fragments and do a further stage of fragmentation on that to give us the MS to the N operation. Ion traps are low resolution mass specs, typically unit mass resolution. In medicinal chemistry, they've tended to be used for compound conformation, and in DMPK analysis, usually qualitative analysis such as metabolite ID, they're rarely used for quantitative assays because the linear range of these mass spectrometers is quite limited in comparison with others. We'll now look at quadrupole mass specs. Quadrupole consists of 4 parallel rods arranged as shown in this picture. To the rods are applied RF and DC voltages with the same polarity on opposite pairs of rods, as shown in this schematic. The polarity is constantly switched between the pairs of rods, which causes the ions to oscillate. This is shown in this cartoon at the bottom of the slide, which shows the ions following a sort of sine wave shape through the quadrupole, although it's probably in 3D, it's probably closer to a corkscrew motion. At each value of RF to DC, only one mass to charge is stable in the quadrupole. All other ions are either hit the rods or are ejected from the quadrupolar region. The instrument can be scanned by linearly increasing the RF to DC ratio to give us a mass spectrum, or it can be operated at a single mass to charge by keeping the ratio constant in a mode known as single ion monitoring. This is extremely useful for quantitative assays. Quadrupoles are low resolution instruments typically operating at unit mass. They have a mass range up to about 2,000 to 3,000 AMU, and they are relatively low cost, although this is relative in mass spec terms. They're also quite robust instruments, and if there is a power outage in a lab, it's typical that you can get a quadrupole back up and run within 2 to 3 hours. In medicinal chemistry, they're used for conformation and reaction monitoring. And in DMPK, they can be used in quantitative assays, although they've tended to be superseded by triple quadrupoles. Before we go on to look at triple quadrupole and high resolution mass specs, we'll look at the concept of signal to noise. This is important as many of the in vitro and in vivo assays used in DMPK require the detection of very low levels of analyte in complex matrices such as blood. The easiest way to measure it is simply by measuring the height of the signal and dividing by some parameter of the baseline noise, such as the peak-to-peak value, or a statistical parameter such as the RMS value. One problem with this approach is that different values can be obtained by measuring the noise in different regions of the baseline. If we divide the signal by the peak-to-peak noise in region 1, we get a signal-to-noise value of around 12. If we use the peak-to-peak noise in region 2, we get a signal-to-noise of around 6, approximately half. Such a subjective measure is not ideal and confirms what you were probably told as a child. You should never pick your noise. If using this simple approach, it's important to be consistent in how the peak height is measured and what region of the baseline is used for noise measurement. Signal-to-noise measurements are typically used for determining limits of detection and quantitation, and generally require measurements of signals obtained in blank samples or matrices. This will be covered in more detail in talks on bioanalysis. So where does the noise come from? Well, a major part of it arises from the ionization process. A mix of background, solvent, and clusters of ions and their associated adducts give rise to a typical electrospray spectrum, which shows a peak at almost every mass. Quadrupole and ion trap mass spectrometers are very sensitive. They give a large increase in signal for an increase in concentration. However, the limit of detection and the limit of quantification for these instruments is often limited by this background noise, and tandem mass spec and high resolution mass spec can be used to reduce this to greatly increase the signal to noise value. A triple quadrupole consists of two single quadrupoles, Q1 and Q3, separated by a collision cell. Q1 and Q3 can act as individual mass spectrometers and do different experiments such as scanning or single ion monitoring. The collision cell usually contains an inert collision gas such as nitrogen or argon to aid in fragmentation. The instrument can be operated in a number of different scan modes, but for quantitation, it's usually used in multiple reaction monitoring, or sometimes called selected reaction monitoring. In this mode, typically, Q1 allows only the parent molecular ion through into the collision cell, and it's then fragmented. Q3 will then monitor the most suitable fragment, which is usually the largest fragment. In this example, which is actually from gas chromatography with an electron impact source, we're going to measure deuterated naphthalene, which has been added to a crude oil sample as an internal standard. On the triple quad, in this case, Q1 is set to 136, which is the parent molecular ion, and Q3 to 108, which is effectively the loss of an ethyl group. This example has a direct comparison between the full scan method on a single quad, the single ion monitoring method on a single quad, and the MRM mode on a triple quad. As you can see with the full scan method, the deuterated naphthalene is barely detectable and is indeed below the integration level set for the instrument. On single ion monitoring mode, the peak is clearly visible, but the background is very high, so our signal to noise is roughly around 10 to 1. If we look now at the multiple reaction monitoring mode, the peak height is much lower than that achieved in single ion monitoring, being only 10 to 20%. However, the background has almost been completely removed, giving a signal to noise of greater than 130. Triple quadrupoles are very robust instruments. They are more expensive than single quads and ion traps, but they are cheaper than the high-resolution instruments such as Orbitraps and QTOFs. They've for years been the gold standard for quantitation in DMPK and bioanalysis, and even now, for most assays, the most sensitive method is usually on a triple quadrupole mass spec. To demonstrate how high-resolution mass spec can help with signal-to-noise, we'll look at a series of microsomal clearance samples. In this case, it's phenacetin run with mouse microsomes. The incubation times are shown on the left. At each time point, the mass chromatogram of the phenacetin at a mass of 180.1 is generated and the peak area measured. The peak area is then plotted against incubation time. And as you can see, the sample is cleared quite quickly. By 15 minutes, there's barely any phenacetin left, so it's close to the detectable level. If you run the clearance samples under both low and high resolution conditions and zoom in on the molecular ion region for phenacetin, at low resolution, we see a single peak for the molecular ion at 180 and a small peak for the isotope at 181. When we go to high resolution, we can see now that the molecular ion peak is resolved into two, and that just next to the main peak is a small impurity peak. This has been magnified for effect, but is present in all scans throughout the chromatogram. We can demonstrate the advantage of high-resolution MS by running the 15-minute incubation sample, which, as we saw in the previous slide, was just above a detectable level under both low and high-resolution conditions. At unit mass resolution, shown in the phenacetin spectra, the mass chromatogram would typically be generated with a 1 Dalton window, that is 180.1 plus or minus half a Dalton. As shown in the chromatogram, the background noise level is quite high. The peak shape is poor and therefore cannot be integrated accurately. By contrast, under high-res conditions, using a narrow mass window of approximately 0.008 of a Dalton, which is roughly plus or minus 20 ppm, the background or impurity ion is now excluded, and on the mass chromatogram there is virtually no noise. The peak shape is good and can be integrated accurately. If we look at high-resolution mass spectrometry and start off with time of flight, ions entering the flight tube from the source are intermittently accelerated by a high voltage applied to the pulsar. This gives the ions a certain amount of kinetic energy and sends them down the flight tube and also starts the timing mechanism. The ions can either be detected at the end of the flight tube or more typically, they are reflected back to increase the flight path before hitting the detector. The reflectron is a series of lenses held at increasing voltages which causes the direction of the ions to change and is there to increase mass resolution. The flight time of the ions is proportional to the mass to charge. To allow a time of flight to be used for MSMS work, a quadrupole is often added between the source region and the flight tube. This acts as a collision cell and allows for precursor ion selection. Time of flight mass specs are capable of very high resolution, 60 to 80,000 for the most modern instruments, and therefore they can give excellent accurate mass and elemental composition data. In theory, the mass range of these instruments is unlimited, unlike quadrupoles where the upper limit is typically 3,000 to 4,000 Daltons. However, they do require a higher vacuum than quadrupoles and are therefore a little bit less robust. If an instrument reaches atmospheric pressure, it takes longer to pump down than a quadrupole and also requires a period of conditioning. In medicinal chemistry, they're used increasingly for accurate mass data, which is suitable for publications. In DMPK assays, they've typically been used for metabolite ID. Historically, the weakness with these instruments was the relatively limited range of the detector. However, this has greatly improved and they are now used in both qualitative and quantitative assays. The last instrument I'll mention is the Orbitrap. It's fair to say that this has revolutionized mass spectrometry since it was introduced over 20 years ago. It consists, as shown in the schematic, of an inner spindle-shaped electrode surrounded by an outer barrel-shaped electrode. A voltage applied to the spindle electrode causes ions in the trap to describe a circular motion about the central electrode, but also a harmonic back and forth motion along the electrode axis. It's the frequency of this harmonic motion which is proportional to the mass to charge. These movements of the ions give rise to an image current on the outer electrode, which give the frequency and abundances of the ions, and a Fourier transform of the image current gives a mass spectrum. Depending on which type of Orbitrap you buy, you can get resolutions of up to 1 million, and the accurate mass is capable of sub-ppm accuracy. They're probably not as robust as the Quadrupole mass specs, they require a higher vacuum, and they are quite expensive. However, for DMPK assays, they can do all the qualitative and quantitative assays that any of the other mass specs can do. And finally, I'll finish with a quote from Benjamin Franklin, who said, "Nothing is certain in life except death and taxes." But I'm sure if he worked in drug discovery, he'd probably say that the third thing that is certain is that a mass spectrometer will break down on a regular basis. And because of that, servicing is as important as the hardware that you buy. And it's worth looking at the service record of the instrument manufacturer in your area. Do they have a high turnover of engineers? That's usually a bad sign. Ask colleagues about their experiences of the servicing, and also ask about the cost of a service plan. These can often seem expensive, but when you take into account the fact that it covers call-out charges and the cost of materials and spare parts, it can work out cheaper in the long run.